Hi, this is Bob Fontana, Alpha Kilo 3 Yankee, and this presentation is on the NanoVNA and some of its many uses in the ham shack. I hope you enjoy, and I hope at the end of the presentation you'll have a better feel for what the Nano can do in your shack. We'll begin the presentation with a brief introduction to N-port linear networks. In particular, we'll look at how to characterize an N-port network using scattering or S parameters. These S parameters, which are parameters that are directly measured by the Nano, can be used for determining such features as return loss, standing wave ratio, gain, and impedance in a linear system. We'll make a brief comparison between antenna analyzers, which many of us have used over the years, and the vector network analyzer, which is a much more powerful tool. We'll look at the hardware architecture behind the NanoVNA. From there, we'll start talking a little bit about Smith charts and how they relate to the display of S parameters and their relationships to the performance of linear systems. Most importantly, though, we'll look at applications of the NanoVNA in the shack. Such examples as measuring antennas, measuring passive networks such as diplexers and filters, using the Nano to determine the design parameters for crystal ladder filters, RF amplifier characterization, gain and impedance values, coaxial cable measurements, determining the characteristic impedance of an unknown segment of cable or its loss versus frequency, using a NanoVNA as a grid dip oscillator, in other words, a tool for measuring the inductance or capacitance of an unknown device in a tuned circuit. Time domain reflectometry, using the Nano as a fault detector, in other words, determining where a break might be in a coaxial cable using the Nano. We'll talk a little bit about matching networks and how we can use the Nano and the Smith chart to perform the matching techniques that we need for a specific circuit. Finally, we'll look at a unique application of the Nano for determining antenna gain and the radiation patterns of an antenna. Let's talk a little bit about N-port linear networks. Well, first of all, what is a linear network? Many of us know what linearity is in terms of amplifier performance. But in general, a linear network is a network in which if I apply an input X and I end up with an output Y, then if I amplify the input by a factor of A, then the output will be A times Y. In other words, the output responds linearly to the input. Also, if I have an input X1, which results in Y1, and an input X2, which by itself would result in Y2, if I add those two together at the input, two-tone test for example, then the output should be Y1 plus Y2. And any deviation from this, of course, is nonlinearity. Now, there are several types of linear networks that can be characterized by the number of ports involved. So, for example, a one-port network is one in which there is a single input. An example of that would be a pure resistance. Here, I've got an input to a device. There's no other way of getting into this device other than that single entry point. Two-port linear networks are things like filters. For example, if I have a LC filter, I apply an input here and I end up with an output. Here's one port and here's a second port. And an example of N-port networks are things like diplexers. Here's a good example of a diplexer right here. So I have one input results in multiple outputs. So how does one characterize an N-port linear network? Here's an example of a two-port network in which I have an input port 1, an output port 2. Across the input port, there's a voltage V1, an input current I1, and across the output port number 2, there's a voltage V2 and a current I2. Since this is a linear system, these parameters, V1, I1, V2, and I2, are related by two sets of linear equations. V1 is equal to Z11 I1 plus Z12 I2, where the Z sub i's are impedance parameters for the network. And equivalently, we can write this in matrix form, which is a little bit more compact, especially when I have N ports, as a matrix Z11, Z12, Z21, Z22. Now, these four complex impedances can be determined by making a few measurements. The first measurement is I set the output current equal to 0. That corresponds to an open circuit on port 2. There's no current flowing into that node. And I measure the voltage to current ratio at the input port. That's V1 over I1. And from that, I can end up with Z11. And you can see that in this linear equation here. If I set if I set I2 equals 0, this term vanishes, and V1 over I1 is purely Z11. It's similar to what you would have with a resistor, for example. The voltage over current is equal to the impedance. The problem with this particular approach, this impedance approach, is that you need to establish open circuits, which sometimes are very, very difficult to generate, particularly when you're dealing with VHF and UHF and microwave frequencies. So this is, while it's an accurate representation of the n-port linear network, it is not an easy one to with which to determine the parameters using physical mechanisms. In the previous slide, we saw one representation of a linear two-port network using impedance or Z parameters. However, there are a large number of different ways of describing a linear system. And another one that is of prime importance here is that of scattering or S parameters. And here's an optical analogy of scattering parameters. Here I have an incident wavefront A1, which impinges on a optical lens, and that incident wavefront is either passed through the lens and generates an output here, or it's reflected off the surface of the lens and ends up with a reflective component B1. The relationship between the incident and reflected wavefronts is called the S parameter. In this case, S11 is the relationship between the reflection B1 and the incident wavefront A1. Similarly, S21 is the relationship between the wavefront that passes through the object and the incident wavefront A1. So that's B2 over A1. And similarly to what we did with Z parameters, we have a matrix representation of the system that can be written in this format. There are these are equivalent to two linear equations. B1 is equal to S11A1 plus S12A2, etc. So the device under test now is going to be looked at from a incident and reflection perspective, and this will be important for measuring distributed systems, as we'll see in the next view graph. In order to measure the S parameters, we'll have to look at these equations one more time. Remember that the B1 was S11A1 plus S12A2, and similarly for B2. So we have an incident wavefront that's either reflected or passed through, and we make a measurement of the ratio of those two incident fronts. So S11 is the reflected wavefront divided by the incident wavefront, and that is determined by looking at B1 over A1 when A2 is equal to 0. So if I set A2 equal to 0, we get a similar equation to what we have with impedance parameters, only now we're looking at incident and reflected wavefronts. Now note that A2 equals 0 means that there is no reflection from the load. Well, what does that mean? In the case of coaxial transmission lines, no reflection occurs when the impedance of the load exactly matches the characteristic impedance of the transmission line. So as you can see, that in order to measure S11, it's a simple matter of properly terminating with the characteristic impedance of the transmission line that's being used. That's quite different and much easier to perform at microwave frequencies than measuring the input currents or output currents at RF frequencies. So the S parameters are particularly useful for measuring distributed systems where the frequencies may be so high that parasitic inductances and capacitance become a very important portion of the measurement process. Here the reflection is set exactly to 0. precisely to zero whenever the impedance of the load matches the transmission line characteristic impedance. As we saw in the previous view graph, S parameters are particularly useful for measuring the properties of distributed linear systems or systems which have very, very high frequency responses. So how does one physically measure a scattering parameter? Well, one example, which many of us are familiar with, is the standing wave ratio bridge. On the left-hand side is the Heathkit SWR bridge, and in this case, there are two parameters which are measured. One is the incident wavefront, which we'll denote by absolute value of A1, and the reflected wavefront, which we denote by absolute value of B1. Note that there's an absolute value there because these are detected values. Note the diode detector capacitive filter circuit, and this ratio of absolute B1 to absolute A1 is the reflection coefficient, or we can compute from that the standing wave ratio. But note that there's no phase information given by this particular configuration. In the second example, we have what's known as a strip line coupler, useful at microwave frequencies, UHF through microwave frequencies. And here we actually get the incident voltage A1, the reflected voltage B1 through coupled ports on this strip line. And by measuring the ratio of these two values and taking proper account of the phase relationship between the voltages, we can end up getting the S parameters as well. The problem with this particular circuit is that it's fairly narrow band and has to be tuned to a specific range. A third approach, which is used in the NanoVNA, is that of the Wheatstone bridge. Wheatstone bridge, you may be familiar with, is a bridge in which there are four components. There's a bridge component here on the left-hand side, another bridge component on the right-hand side. And when the ratio of these two resistors is equal to the ratio of these two resistors, there's no current flow through the center resistor. So that bridge is balanced at that point. And it turns out that the current through this resistor, you probably can't see it, but it's R5, is directly proportional to the reflection coefficient at test point R4. This is test point R4 right here. So it's an extremely useful approach to measuring reflection coefficients. What's particularly nice about it is you notice that it's entirely resistive. And so the possible frequency range of this is quite extended. It can go up through multiple gigahertz of bandwidth. And the Wheatstone bridges are what are used in the NanoVNA for measuring the reflections. So now that we've determined the S parameters of a system, what can we do with them? Well, a couple common quantities that we're very familiar with can be determined in terms of S11 and S21. For example, the return loss is given by -20 times the log base 10 of the absolute value of the S11 S parameter. The Heathkit SWR bridge that we saw earlier calculates its standing wave ratio as the ratio of 1 plus absolute value of S11 over 1 minus absolute value of S11. Remember that we measured the incident and reflected voltage amplitudes in that specific bridge configuration. Note in both these cases, in the return loss and voltage standing wave ratio, there is no phase information. Same thing true with system gain. System gain, which is the transmission gain through a system, or sometimes transmission loss, depending upon whether or not we have a linear network which is lossy or an amplification which can provide some gain, is given by 10 log the magnitude of the S21 S parameter. And finally, the impedance that we see looking into a port is given by this particular relationship. The impedance is equal to the characteristic impedance of my network times 1 plus S11 over 1 minus S11. Note that S11 is a complex quantity, and so Z is a complex variable, whereas in the three previous cases, we are dealing purely with magnitudes. The S11 can be also written in terms of the impedance by inverting this equation, and we see that S11, which is also referred to as gamma, is given by the ratio of Z minus the characteristic impedance divided by Z plus the characteristic impedance. Note that the reflection coefficient amplitude or magnitude is always confined between 0 and 1. As mentioned earlier, there's a difference between a standard antenna analyzer and a vector network analyzer. Antenna analyzers typically are designed to measure a single port or two-terminal network, antenna input, things of that nature, and they measure antenna standing wave ratio and sometimes the driving point impedance. For example, the Rig Expert AA600 will provide that information. Unfortunately, with an antenna analyzer, you cannot remove the effects of connecting cables or intervening low-pass or high-pass filters, etc. On the other hand, a vector network analyzer can measure two-port or four-terminal networks, and the antenna visuar and driving point impedance can be determined just as with the antenna analyzer. However, in this case, we can also measure such things as filter parameters, small signal transistor parameters, multi-port networks, duplexers, diplexers, transmissions lines, etc. And the advantage of the vector network analyzer is that through the calibration process, we can effectively remove the effects of connecting cables and other passive circuitry. Also establish a particular measurement plane at which measurements are performed. The system block diagram of the NanoVNA is actually quite simple. The input is a resistive Wheatstone bridge, as we discussed earlier, a very nice broadband device that allows the measurement of both transmitted and reflected power or voltages. The output of the Wheatstone bridge is passed to a set of Gilbert cell double balanced mixers. The local oscillator for the NanoVNA H version is established by a clock synthesizer chip, the SI5351A. The SI5351A generates a square wave output, so there's a lot of harmonic content, and in fact the NanoVNA H uses that harmonic content to allow computations at higher RF frequencies. The outputs of these double balanced mixers are passed to are down converted to audio, and in fact they're processed by a stereo audio codec, the TLV320. That is controlled through an I2S interface by the Cortex-M0 48 megahertz CPU. And there's a SPI, a serial parallel interface, a liquid crystal display as well. It's a nice compact architecture. It has the advantage of simplicity, low cost, but it has a disadvantage in that the dynamic range is going to be tailing off with higher frequencies due to the fact that the synthesizer generator is basically working on its harmonic content. Let's talk a little bit about the Smith chart, as it'll become useful later when we talk about matching networks. The Smith chart is simply a plot of the complex reflection coefficient gamma, which is also S11, overlaid onto an impedance or admittance grid, and all this is referenced with respect to a 1 ohm characteristic impedance. As we talked about before, gamma, or S11, is related to the complex impedance that's being measured by this relationship. Gamma is equal to Z minus Z0 over Z plus Z0. So if the impedance that we're looking at is exactly equal to the characteristic impedance, Z equals Z0, then the numerator term goes to 0, gamma is 0, and we find ourselves at the origin of the Smith chart. The normalized impedance at that point is Z, which is 50 ohms, divided by the characteristic impedance, which is also 50 ohms, which is a value of 1. So gamma equals 0. Remember that gamma is a complex number. The magnitude of gamma and the phase of gamma determine where it is on the Smith chart. So for example, if I have an impedance of 50 ohms in series with 227 picofarads, at 7 megahertz, this corresponds to an impedance of 50 minus J 100 ohms. Normalizing this by dividing by the characteristic impedance, in this case 50 ohms, I get a value of 1 minus J2, and that corresponds to this location on the Smith chart. So from that location, I can determine what the angle is, I can determine what its magnitude is, and from those information pieces, I can get things like standing wave ratio, etc. Let's look at the Smith chart a little bit more closely and look at 3 specific points on the graph. In particular, we're going to look at the center where gamma is equal to 0. Remember, that corresponds to 0 reflection. And since we have 0 reflection, that must mean that we have an impedance which matches the characteristic impedance of our transmission line. We have the right-hand corner of the Smith chart, which corresponds to an open circuit. That's at gamma equals +1, where I get complete reflection coming back. And on the left-hand side of the Smith chart, I end up with a gamma of -1, which corresponds to a short circuit or a normalization value of 0, and complete reflection with 180 degrees phase shift. At the upper part of the Smith chart, above this horizontal line, which is the resistive axis going from 0 ohms on the left-hand side to infinity on the right-hand side, I end up with all the possible impedance values which have an inductive component. On the lower part of the Smith chart, I end up with all the possible impedances which have a capacitive component. So by looking at a point on the Smith chart, I can tell whether it is inductive or capacitive and whether its resistance is. Now, the way that the vector network analyzer does its calibration is by trying to assign the correct adjustment parameters so that the values that are measured with a short circuit, a load, and an open circuit fall along these 3 points on the Smith chart. So this is called a short, this is an open, and this is a load. So what you'll see is a short, open, load calibration occurs when I place a short circuit on the output of the network analyzer and measure what the gamma coefficient is. I place a 50 ohm load at the output of the port and look at where it falls on the Smith chart. Hopefully that falls in the center. And similarly, I place an open circuit on the output of the port and look at where that reflection coefficient is measured. If they don't fall on these 3 points and along this axis, then the parameters of the network analyzer are adjusted until they do so, and that's the calibration process. One interesting consequence of the nonlinear mapping that occurs between impedance and the reflection coefficient gamma is that for a fixed voltage standing wave ratio, I end up with a circle that appears in the Smith chart. So every single impedance that lies along this circle, for example, has a standing wave ratio of 2:1. Similarly, all the points that lie along this circle have a standing wave ratio of 1.2:1. If I fall at the center of the Smith chart, I know that my standing wave ratio is exactly 1:1 because that's the point where gamma is precisely equal to 0. So as you can see, it's very easy to look at the trajectory of a set of impedances from a measurement that one might make on an antenna or a filter design, and from there establish what the standing wave ratio is as a function of frequency. So to reiterate, why do we want to use the Smith chart? The Smith chart, as we saw, is a very nice graphical method for visualizing the complex impedance, reflection coefficient, and voltage standing wave ratio of a linear system as a function of frequency. We'll find later that it's extremely useful for designing impedance matching networks. And one thing nice is that there is available a interactive Smith chart program from AE6TY, the reference is provided here, that allows you to take NanoVNA data, which is exported in what's called a touchstone file format, and process it within SimSmith. A very useful application. The curve that you see here is the measurements that were made on a MyAntenna's EFHW end-fed half-wave 80 through 10 meter antenna at MyQTH. covering the 20-meter band and we're looking at 13 through 15 megahertz. And you can see that the antenna is nicely resonant near 14 megahertz. Remember that closer you get to the center of the Smith chart, the more closely you are to an SWR of 1 to 1. So how do we use the NanoVNA? Well, first of all, as I mentioned earlier, we need to perform a calibration. And the purpose of the calibration is to align the S11 measurements. Remember, S11 is the gamma coefficient, which represents the angle and phase of the impedance on the Smith chart. And we want to align the S11 measurements with the purely real -1, 0, and +1 positions on the Smith chart. Remember, -1 corresponds to a short circuit, 0 corresponds to a 50 ohm load, or a load which matches the characteristic impedance if it's not 50 ohms, and +1 corresponds to an infinite resistance but 0 reactive component. We also want to, in the case of a two-port measurement, we want to properly normalize the S21 measurement in order to provide the correct relationship between the output voltage and the input voltage as passed through the NanoVNA. This is done to account for such things as cables, connectors, other devices which might be inserted between the device under test and the VNA, such as a filter. Maybe I want to put a 20 dB pad, as we'll see a little later when we're measuring some amplifiers. You might want to look at the output of a matching network and look at the impedance of the antenna at that point. So by calibrating, by placing a reference plane at the point where you'd like to make a measurement and assigning a open 50 ohm load and a short at that point, we can then calibrate out the effects of intervening connectors and cables and what have you. Now, when should this calibration be done? Ideally, you want to perform a calibration whenever the frequency range of interest changes. Secondly, you want to make a calibration run whenever you've made significant changes to your measurement plane. So for example, if I want to measure at one point on a filter, let's say on the input of the filter, and I suddenly want to now look at what happens on the output of the filter, I may want to recalibrate at that spot if I want to measure that impedance at the output. Also, in general, if components vary by more than a quarter wavelength to a half wavelength in dimension, in other words, if I add another quarter wavelength or half wavelength of coaxial cable on a run, I might want to redo the calibration run. In my QTH, I typically calibrate every time I make a measurement. It doesn't take very long to do, but if I'm going to make a series of measurements on a set of cables or a set of antenna designs, usually the calibration run, as long as I don't change the frequency range of interest, will last weeks, if not months. Also, there's a set of software programs available which allow you to interface directly with the NanoVNA, and these are quite useful because they'll extend the size of the screen substantially. These things are pretty tough to use since they're so tiny. At least if you have fat fingers like I do, it's difficult to operate. The NanoVNA Saver software is a great piece of software. It allows you to see the screen much more in detail on your own computer screen. But it's also, what's nice about it is you can perform calibrations through that software. And I very much recommend that if you're going to use NanoVNA software or other software, that you perform the calibration runs within that software itself, rather than doing it on the NanoVNA itself. There are a lot of advantages to doing it in software. One particular advantage is that often these NanoVNAs are limited to 100 or 200 data points, depending upon the design. And in software, you can extend that to literally thousands of data points. So the steps in calibrating the NanoVNA are quite simple. The first step is to determine the frequency range of interest. If you first turn the NanoVNA on, you'll see that it spans from near DC to its maximum range. The problem is with the NanoVNA directly, without using software, the nano is only limited to 101 data points. So if I'm going to span from 0 to 1.5 gigahertz, for example, then each data point corresponds to 15 megahertz, and it's very easy to skip over a particular frequency range of interest, thinking that you've got a very nice SWR, but you never really made a measurement at that point. So the best thing to do is determine the frequency of range of interest and limit your calibration to this range to provide better accuracy. The second step is to determine the measurement plane. This is the point where the characteristics of the device under test are to be measured. So if I have an antenna and I want to look at the effects of the antenna alone and not the cable leading to the antenna, then I want to have the measurement plane at the far end of my cable. And by that I mean I'm going to do a short open load calibration at the end of the cable where it attaches itself to the antenna. If I want to look at the performance of the entire system, including the coaxial cable, then I might want to perform a measurement or a calibration with the measurement plane at the input to the coaxial cable. We'll see more of that as we go along. On the NanoVNA, always perform a calibration reset first. This is sort of a glitch that occurs in several of the NanoVNA designs. If you perform a calibration reset, you won't have problems calibrating the unit. Sometimes the calibration just doesn't stick properly. Again, we'll perform a short open load calibration process, applying a short circuit, open circuit, and load of 50 ohms to the calibration port, or to the measurement plane attached to the calibration port. These devices, short, open, and load, are usually provided with the Nano. The NanoVNA-H, for example, has a set of SMA connectors that one is a short circuit, one is an open circuit, one is a 50 ohm load. And there's also a barrel that is used for through measurements, and that's attached between the cable runs from the single port that generates the output to the port that's accepting the input, port 1 and 2. Again, in the NanoVNA Saver software, use the calibration assistant to provide the calibration run for you. Don't forget to save your calibration results. The NanoVNA, use one of non-volatile memory locations. Save your calibration files to disk. And again, the calibration runs usually remain quite good if your configuration has not appreciably changed. In other words, less than maybe a tenth of a wavelength or a quarter wavelength in dimensional changes. So now that we've calibrated our NanoVNA, let's take a look at some applications. First application, which I think most people use the Nano for, is measuring antenna performance. And by that I mean looking at the standing wave ratio that exists at the input to the antenna. Here's an example of a M² Leopac 2-meter beam. It's a 4-element horizontal, 4-element vertical circularly polarized array, used primarily for satellite applications. And the range of interest was from 144 megahertz to 148 megahertz. So I set up the NanoVNA so it calibrates only over that specific range. What I did next was I generated the S11 characteristics, which occur automatically on the Nano, and I downloaded them to a touchstone file, which is called a .s1p file in this case. These were then loaded into SimSmith, and here you can see a depiction of the trajectory of the impedance of that M² Leopac antenna as a function of frequency. I've plotted here the SWR equals 2 and SWR equals 3 circles, so you can see that the performance is actually quite good as I get closer to the low end of the band, which is a satellite portion of the band. And here I've also plotted the standing wave ratio on the right-hand side. This is a standard application. I think most people use the Nano for this, but there's so much more that can be done with this particular instrument. Let's look at another example of a one-port network. In this case, I have an NFED transformer. The NFED transformer is designed for a 49:1 impedance transformation, and it's attached to an NFED wire, typically a half wavelength at the lowest operational frequency. This is a commercial unit from myantennas.com, but you might have one that you built in the shack and you wanted to determine, is in fact what I just built 49:1? Is it working properly? Well, how do I determine that? A simple way of doing that is to see if we actually get that transformation of a non-inductive load to 50 ohms. So in this case, what I did was I took a 2400 ohm carbon composition resistor and applied it to the output port of the NFED. The input port of the NFED is passed to my NanoVNA. So the measurement plane is right here. In other words, I'm going to do a short open load calibration run with the short, open, and load elements applied right at this point. Once I've done that, then I take out the effects of this little piece of coaxial cable and I can look at the performance of the transformer. Ideally, if the transformer was in fact doing its 49:1 ratio, then roughly 2500 ohm resistance on one side should give me 50 ohms on the other, and with 50 ohms I should get an SWR which is 1:1. Well, I don't quite get that. As you can see, the SWR is floating around 1:1 or maybe around 2:1, and this is the location of the impedance values for that NFED transformation or the transformer transformation. Here is the actual plot of the magnitude of the impedance. This is 50 ohms here. You can see it falls a little bit below 50 ohms and at lower frequencies, and then it moves up sharply on the high end. The standing wave ratio is still below 2:1, which is not bad. Now, a couple of things to point out. One is at the higher frequencies, this little piece of wire turns out to be more and more problematic in terms of its inductance. So if I wanted to do this very, very carefully, I would have used a very thick braid here to minimize the inductant reactance that I would have at the higher frequencies. So this climb that you see here, it may not be due to the transformer. Also, the one thing I should point out is that I cannot test using the NanoVNA such things as the transformer's ability to handle high power, whether it saturates or not. The power levels coming out of the NanoVNA are quite small. But in general, what I see here is that sure enough, my 49:1 transformation is doing quite well. I'm getting an SWR which is better than 2:1, and it seems to be flat over the entire frequency range from 3 to 30 megahertz. What I also did was I made the same measurement. Now, instead of applying a 2400 ohm load, I actually attached my 132-foot half-wave wire at 80 meters. And you can see this is a plot of the standing wave ratio as a function of frequency. The interesting thing about the NFED antennas is they provide very, very nice resonances or low SWR at integer multiples of the fundamental half-wave frequency. In this case, 80, 40, 30, etc. Now here's an example of a two-port measurement. In this case, I have a triplexer that's designed for 2 meters, 70 centimeters, and 23 centimeters by Diamond MX3000N. And what I want to do is look at what its performance is as a function of frequency and what the cross terms are. In other words, how much energy goes from the 2-meter side into the 70 centimeter side and vice versa, or between the 23 centimeter side and the 2-meter side. Let's look at the attenuation that's out of band for the triplexer. So what I did here was port 1 of the NanoVNA is the output port, which is providing a signal to the input of the triplexer. The output of the triplexer, and this is a 2-meter, this is a 70 centimeter, and this is a 23 centimeter port. I load the 70 and 23 centimeter ports with 50 ohm terminations. The triplexer will not work well if those other ports are not terminated. And what I do is I take the output of the 2-meter port and pass it into port 2 of the NanoVNA. So what I'm measuring here is S21. In other words, the transmission coefficient going between port 1 and port 2. If I make this measurement over frequency, then I end up with this curve here. You can see that the 2-meter response, as the signal excitation starts getting higher and higher in frequency, the output from the 2-meter port drops substantially. And at 70 centimeters, I end up with a 53 dB of suppression or out-of-band suppression in this triplexer. Similarly, if I I ground the 2-meter port to 50 ohms, or I should say attach a 50 ohm load to the 2-meter port, look at the 70 centimeter port on port 2, and again put a 50 ohm load on the 23 centimeter port, I end up with this curve. And you can see again that at 2 meters, I end up with 50 dB of suppression. Now, the manufacturer specifies 55 dB suppression or isolation in the ham bands. I'm not quite getting that. I'm close, minus 53 and minus 50. The question is, why am I a little bit off? Well, it turns out that the dynamic range of the nanos are really, good, but not good enough to get me down to the point where I'm measuring things below 55 or 60 dB of attenuation. So, for example, the SAA2N NanoVNA has a noise floor of 50 dB or better below 1.5 gigahertz and slightly better below that. Here's another example of a 2-port linear network. In this case, I've got a ceramic resonator filter. This consists of 3 ceramic filters, or 3 ceramic resonators, I should say, at 500 kilohertz, and a set of capacitors which allow me to tune this for the desired response. The thing to take into account here is that I want to eliminate the effects of the coaxial cables and connectors attached to my filter. And so I set up the measurement planes in such a fashion that my short, open, and load through calibration runs are done at these 2 points. So for example, I will apply the short, open, and load at this location here, and then I will connect these 2 pieces of cable together. I should say the one cable to this barrel. I'll connect this together here, and this will be my through run. In other words, bypassing the filter itself. In doing so, that gets rid of all the effects of this little cable, this little connector here, this coaxial cable run, this connector, and also this barrel. That's important. Less so at very low frequencies, very important at UHF, VHF, and certainly higher microwave frequencies. In this case, the filter was swept between 490 and 500 kilohertz, and you see the results here. This output was performed again using the NanoVNA Saver software, downloading that to a file which is then plotted. You can see the same results here, but it's somewhat difficult to get very precise measurements on this. You can do that with a little thumb wheel switch on the top, but in general, it's nice to be able to use your computer to look at the results more carefully. When you're out in the field, of course, it's more difficult to lug around a laptop, but in general, I tend to like to attach the computer to the Nano and use the Nano as a standalone instrument. Here's another example of a 2-port linear network, and this is a crystal filter in this case. However, in this case, what I want to do first is determine the parameters of the crystals so that using those parameters, we can design the ladder network. So to do so, I want to look at the crystal model, and the crystal model is shown here, which consists of a motional inductance, a motional capacitance, and a parallel capacitance, which represents the case and the connecting items to the quartz itself. To measure these 3 parameters, we're going to use the Nano in kind of a unique way. We're going to look at the impedance that is seen by the Nano and look at the points in the impedance where we get an abrupt change due to the resonance effect of the crystal. In order to measure these 3 parameters, we'll need 3 equations, basically. And we have 3 unknowns, 3 equations will do it. So the way to do that is we're going to apply an external capacitor, and the external capacitor will have 3 values, selectable values, 0 puff, 10.3 puff in this case, and 30 puff. Those are the values that I measured that I had available. The NanoVNA is set up as in the previous example, where we have a measurement plane that occurs over here for the output and over here for the input. And the crystal is in between. We're going to look at the impedance of this entire network as a function of frequency. And in the three cases of 0 puff, 10.3 puff, and 30 puff, we're going to measure the resonant frequencies that we see. To do that, we're going to take and measure S11, but instead of displaying S11 as a vector on a Smith chart, we're going to look at the real and imaginary components of it and look at where that imaginary component goes through the origin. Alternatively, we could look at the peak value here. We'll see the resonance occurring at the position where the imaginary part goes through 0. There'll be a peaking effect in the other component. So at 10.3 puff, for example, the nano sweeps through and we can see a resonant frequency of 18.003158 megahertz. I do that for all three parameters, and using those resonant frequencies, then I can plug them into a formula to get the three component values that I need for completely defining the crystal itself. Once I have those three parameters, in particular the motional inductance, the motional capacitance, and the parallel capacitance, and I got that by looking at the resonant effects of those crystals by sweeping the NanoVNA across the frequency range from about 17 to 19 megahertz. Once I have those three parameters, I can place them into a crystal ladder filter calculator, and the references to that were in the previous view graph. Those parameters then will generate a set of capacitor values, in this case roughly 150 puff, 150 puff, and 115 puff for the shunting ones. And I got these by determining what kind of bandwidth I wanted and the number of crystals that I was going to use. Here I'm using 4 crystals. I needed a bandwidth of roughly 3 kilohertz, and I plugged them into that equation or into that software program, and I ended up with this result. Quite accurate, actually. The 3 dB bandwidth of the design parameters were 3 kilohertz. I measured my actual filter to be 2.97 kilohertz. You see the center frequencies match very, very closely. The 6 dB bandwidth is very, very close, etc. So this is a great use of the Nano for building ladder filters that you can use in your existing ham equipment. Here's another example of a 2-port network, in this case an active one, in which we have a RF amplifier that we'd like to look at its gain performance versus frequency. In order to do this, we have to take into account a couple issues. The first one is that the output of port 0 of the NanoVNA comes out at approximately plus 15 dBm. Now this can be adjusted on a few different variants of the Nano, but in general you're looking at somewhere between plus 5 and plus 15 dBm. If you have an amplifier that you'd like to measure, the gain of that amplifier will amplify that port 0 signal to a level that may or may not be compatible with the input levels that port 1 can handle. So in order to make sure that, first of all, the amplifier does not saturate the output port or damage it, and also to make sure that the amplifier itself operates in its linear region, we add a input attenuator. In this case, I've added 20 dB pad between port 0 and the input of the amplifier on the test. So in order to make this measurement, what we're going to have to do is set the measurement plane to be here for the input plane and the output plane to be on the other end of the amplifier. In doing so, by putting the short open load at the output of the 20 dB pad, we remove the effects of the 20 dB pad, and similarly we remove the effects of the coaxial cable at the output of the amplifier when we make these measurements. So here's an example of a very inexpensive amplifier. I think I paid about $9 or $10 for this on eBay. It was specified to have a good frequency response up to around 3 gigahertz or so. And sure enough, it does reasonably well. It uses a gas-FET amplifier chip inside, or amplifier transistor. And so it has a fairly low noise figure. I was not able to measure the noise figure, obviously, with this particular setup. But the gain curve you can see here varies from about 26 dB gain at 2 meters down to around 9 dB gain at 2300 megahertz. Not bad for a little $10 part. So looking further at the amplifier that we looked at in the previous view graph, I'd like to measure the input impedance of this amplifier versus frequency. The test setup is shown above in that it consists of the NanoVNA with its output port 0 applied directly to the device under test. And on the output, in order to dissipate any power, this is a low power device, but in general, for a higher power device, we might want to put a pad and a 50 ohm load to provide a very, very good 50 ohm impedance to the output of the amplifier. One thing you need to take into account is that certain designs may have DC voltage present at the input. And if that is the case, you want to be careful that you don't damage the VNA's output port. To do so, you might have to add a DC block. In this case, we didn't need that. There's no voltage being applied there. And the measurements, as you can see, were made from about 20 megahertz on the low end to 3 gigahertz on the high end. And approximately at 227 megahertz, we'll see that the standing wave ratio has reached a value of 2 to 1 or less. From the Smith chart, you can get the real and imaginary components of the input impedance. Another interesting application for the NanoVNA is the measurement of characteristic impedances on transmission lines. This may be an unknown piece of cable that you have laying around that you'd like to know something more about. From transmission line theory, if I have a quarter wave line, in other words, a line whose length is equal to a quarter wavelength at the frequency of operation, then the relationship between the load impedance and the input impedance is given by this equation here. Z load over Z naught is equal to Z naught over Zn. On the Smith chart, essentially that is a flip along the axis, the horizontal axis of the Smith chart. From this equation, I can calculate that the characteristic impedance of that specific piece of quarter wave line is equal to the square root of the load impedance times the input impedance. Okay, so what we're going to do now is we're going to attach a 50 ohm load to this unknown piece of coax. And here's the 50 ohm load here. I'm going to perform a short open load calibration at this spot on the device under test. And what we're going to do is look at the Smith chart as a function of frequency. At 0 hertz, in other words, at DC, you expect to see exactly the 50 ohm impedance, and sure enough, we do. We lie at the center of the Smith chart. As the frequency increases, you'll see that the trajectory on the Smith chart traces a circle, and there's some point at which the curve intersects the horizontal axis again. Remember, the horizontal axis is pure resistance. So at this point, we know that we have a quarter wavelength. That's the first time it passes through the horizontal line. That is the first time that it reaches a quarter wavelength. It'll do the same thing at a half a wavelength. It'll go back to the this portion here. Another 3/4 of a wavelength. It'll again pass again through this point on the right. But at a quarter wavelength, we'll notice that there's a transition where it turns into a pure resistive load. And at that point, we know we have a quarter wavelength. Well, the quarter wavelength, it occurs at some frequency. We've swept this thing from, say, DC to 100 megahertz or so. And it turns out in this specific case, we see that the quarter wavelength occurs at 25.9 megahertz. And the impedance at that point is equal to 108 ohms. So now we have all the parameters we need to measure the characteristic impedance of this piece of line. 108 ohms at 25.9 megahertz. Z naught from the above equation is given by the square root of 50 times 108, the square root of load impedance times the measured input impedance. That turns out to be 73.48 ohms. So you'll notice immediately I know I have a 75 ohm piece of coax. And that's sort of obvious from the fact that it was provided with F connectors on it. The length of the coax I measured at 73.5 inches, or 1.867 meters, and that should be a quarter wavelength. Well, that in free space would have corresponded to 40.17 megahertz. So if I look at a quarter wavelength in free space, that frequency should have been 40.17, but what I'm measuring is 25.9, which means that the speed of electron flow in this cable is slowed down by the velocity factor of the cable. The ratio of those two frequencies, 25.9 to measured frequency to 40.17, is the velocity factor. In this case, it's 0.654. Well, it turns out that RG59U meets those specifications nearly exactly. The impedance of an RG59U cable is 73.5 ohms. I've measured 73.48, can't get too much closer. And the velocity factor is 0.66. I measured 0.654. So you can see that we have now determined that that hunk of cable that was laying around was a piece of RG59U or something equivalent. Another measurement that we can make on coaxial cables using the NanoVNA is its loss characteristics versus frequency. Remember that S11 is a measure of return loss. In other words, it's the amount of loss that occurs when the wavefront moves out along the cable, bounces off the load, and comes back to the input port. So that round path loss is called a return loss. So if I measure S11 on a piece of cable with a short circuit, where all the energy should have been reflected back, and I measure S11 with an open circuit, again, where all the energy should be coming back, I should get two estimates of what my two-way path loss is. So what I'm going to do is going to average those two out. I'm going to take the 20 log of S11 for a short circuit and divide it by 2. That should be the one-way path loss in the upper example, example number 1. And the second term is 20 log of S11 with an open circuit divided by 2, and that's the one-way path loss with the second measurement configuration. Now, why did I do two different ones? Well, it turns out that if I have a coaxial cable and apply a load to it, you'll see some rippling effects because of the way the impedance varies along that line. So in order to eliminate those little ripples that occur, if I average these two out, one with an open, one with a short circuit, I end up with a fairly smooth line, as you can see on the right-hand side. I've taken a piece of RG223U that I had laying around, and I looked at the loss as a function of frequency by looking at S11 with a short, S11 with an open, and doing this averaging approach. The actual published values for the loss are these little red dots here, and you can see they lie pretty much along what we've measured. So we have got a very good estimate of what the path loss is for this particular piece of coax. Note that in this reddish region on the right-hand side, there's a lot of variation that occurs, and this is due to the fact that the NanoVNA H that we're using here uses the harmonic content of the SI5351 internal synthesizer, and as a consequence, it has a much lower dynamic range, so we're going to be getting a little bit more noise effects on the higher frequencies. So above 300 megahertz, we're going to see a little more rattiness in the measured response, at least with this particular NanoVNA. The SAA2 will do a little better job since it has a much higher dynamic range in that upper frequency range. Now, one device that's very useful when you're constructing electronic circuits, particularly tuned circuits, is a grid or gate dip oscillator. The principle behind that is that there is an oscillator with a loosely coupled loop attachment to it that couples into a resonant circuit. And when the frequency of the oscillator reaches the resonant frequency of the circuit, a certain amount of energy is sucked out because of the resonance, and it causes a dip in the response, whether it's in the grid response on a vacuum tube or in the gate response on a FET oscillator design. Well, we can do the same thing with the NanoVNA. Here I've constructed a small loop of wire that's attached to an SMA connector, and that is attached to the port 0 of the NanoVNA. No need for calibration here because all I'm looking for are subtle changes in the response versus frequency. So what I've done here is I've coupled loosely that loop of wire to a coil, and you can see the coil here, which is just a wound coil on a piece of ferrite material. No capacitor applied to it, so you would not expect a very low resonance, but it turns out that there is a self-resonance that occurs on this particular coil, and we can see that right here. If you plot S11 as a real and imaginary component, you will see a sudden change, a very abrupt change in the impedance value as a function of frequency. At that abrupt change, you've reached the resonant frequency of that tuned circuit or that circuit. So what we notice here is that the coil is self-resonant roughly at 250 megahertz. I took an old Millen 9661 grid dip oscillator and did the same experiment, and sure enough, it lines up right on 250 megahertz. So again, resonant circuits produce an abrupt impedance discontinuity, and you can measure that by loosely coupling the NanoVNA to that resonant circuit. No calibration is needed. Just need a sufficient number of points that you're going to have for the display so you get reasonably good resolution. This is a very useful technique for determining a self-resonant frequency of things such as amplifier plate chokes, tuned circuit frequencies in receiver transmitter stages, etc. Be cautious though, particularly if you're measuring plate circuits, that you're not applying any voltage, because you don't want to get zapped by something or by accidentally touching a high voltage circuit. So again, a warning, just be careful when you're using this around any power circuits. Here's another interesting application for the NanoVNA, and this is time domain reflectometry. What we're looking at here is the time response of a assembly using a impulse or pulse excitation. So in this case, I have a cable assembly that's under test, and I want to look at its response versus time with a pulse excitation. Why do I want to do this? Well, if I have a discontinuity anywhere along this cable, let's say there's a little bit of a shield problem here, or there's a short circuit, then if the pulse travels down this transmission line, portion of that energy, possibly all of the energy if it's a short circuit, will head back to the load. And if I can somehow measure the time of flight of the wavefront as it hits that discontinuity and comes back, by knowing the propagation speed in that cable assembly, I should be able to determine the point at which the cable is broken or cable has got a short circuit. If the cable is terminated with its characteristic impedance, I would expect to see no reflection coming back, or a very small amount of reflection. And the way that people have done this in the past is by using a step response or an impulse response generator and looking at the response on an oscilloscope. Here are some oscilloscope patterns, for example, when you have various conditions on the transmission line: an open response, short at the cable end, matched impedances, etc. So what we're going to do is we want to generate a impulse or a fast rising pulse waveform, observe the reflections versus time on an oscilloscope, and from that determine the position of the discontinuity. One of the difficulties, of course, is generating and measuring these pulses. The finer the pulse, in other words, the shorter duration of the pulse, the finer the resolution we can measure the time to. So we're looking at things which are in the several hundred picosecond range. Not easy to do in the lab. So what we'd like to do is see if we could use the fact that we're measuring the return loss of this cable as a function of frequency, and is that somehow related to the time response of that cable with a pulse excitation. Now, there's a very important relationship between time and frequency. Remember that S11, as we've measured it so far, has been in terms of frequency response. In other words, I look at amplitude and phase of the reflection as a function of frequency. However, the frequency response can be converted into a time response through the Fourier transform relationship between time and frequency. The frequency response of any waveform f of t can be obtained by the Fourier transform f of f, which is the integral of f of t e to the minus j 2 pi ft. And conversely, the time response of that frequency response f is obtained by the inverse Fourier transform integral of f e to the plus j 2 pi ft. This is a Fourier transform pair. If I have f of t, little f of t, I can get capital F of f, and conversely, I can get little f of t from capital F of f through the inverse transformation. Now let's look at a linear system. And a coax line with a discontinuity at the end, or an impedance at the end, is one example. So what I'm going to do is apply an impulse excitation, x of t, to my linear system, which I'll describe by its response h of t, which is sometimes known as the impulse response. We'll see why in a second. And that's going to generate an output y of t. The relationship between the output of the linear system and the input to the linear system x is given by this convolution integral. Y of t is the integral of x with h, and h is the impulse response. And the reason it's called the impulse response is that if I apply an impulse x to this system, then the impulse's Fourier transform is unity for all frequencies. That's the characteristic of an impulse. And in the time domain, in the frequency domain, the frequency response of this convolution integral is the product of the input frequency response, x of f, and the frequency response of my linear system. Well, if x is exactly 1, then the output y is exactly h. In other words, the impulse, the response to an impulse is h of t. That's why it's called the impulse response. And in the frequency domain, y of f is equal to h of f. So if I can apply an impulse like we did in the previous view graph, then propagate it down the linear system, or the transmission line in that case, I should be able to determine both its frequency response and time response. S11 is the frequency response of that reflection. And we're going to see how we can now use that with an inverse Fourier transform to look at it in the time domain. So how do we do this? With a vector network analyzer, we're going to set up an excitation signal, and this is going to be in the frequency domain, where we cover from near DC to some frequency f max, where f1 over f max is the desired time resolution. So if I have 1 gigahertz for my maximum frequency, the reciprocal of 1 gigahertz is around 1 nanosecond. The speed of light in free space is about 1 nanosecond per foot, so 1 nanosecond gives me about 1 foot resolution. The number of sampling points, n, gives me the maximum amount of time that I can look at that reflection over. So for example, if I have 1,000 data points and my resolution is 1 nanosecond, then I'm going to have 1 microsecond of time resolution, 1,000 times 1 nanosecond. So the way we're going to do this is we're going to measure S11, and that's always going to be a function of frequency on a NanoVNA. We're going to inverse Fourier transform that. I don't expect you to do that directly, but their software is available in, for example, the NanoVNA software that does this for you. We'll convert that from the frequency domain into the time domain by using the inverse Fourier transform, and then we're going to plot that S11 of t, which should now show any discontinuities in the reflection coefficient. In other words, it'll show impedance changes, abrupt impedance changes as a function of time. We're obtaining the system's impulse response. Now, in order to convert those time measurements into distance, we have to take into account the velocity of propagation. So as an example, for RG8X, I end up with a velocity of propagation of 0.84 times the speed of light. For RG213, I get 0.66 times the speed of light, always a function of the dielectric material that is being used. So let's look at an example of a TDR response. In this example, I've taken my NFED antenna configuration and applied the NanoVNA to it to look at its response versus time. So what I have is a NFED antenna, 132 foot long, going through a my antenna's 49:1 transformer. That is followed by a 73-foot run of RG213 to the outer wall of my shack, at which point there is a alpha delta coaxial surge protector. Another 22.5-foot run of RG213 within the shack going to my alpha delta coax switch, which allows the antenna to be used on multiple rigs. And then I have a small jumper cable that I use to connect the NanoVNA to the alpha delta coax switch. The measurement plane is right here at the end of the NanoVNA, and I do a short open load calibration at that point. Now, if I look at the S11 in the time domain using NanoVNA Saver software and the TDR response, I notice a couple interesting phenomena. One is there's a very strong reflection, as I would sort of expect at these three different discontinuities. At the alpha delta coax switch, which was roughly 3.5 feet out, I see a very strong reflection. At the alpha delta coax surge protector, I see another set of reflections. Notice that there are a number of them here, and yet you would expect just a single one from that coax surge protector, certainly at low frequencies. Well, these other effects here, these other ripples, are due to windowing effects in the Fourier transform because of the finite range over which we're making the measurement and the fact that we're not quite starting at zero frequency. We're starting off at 100 kilohertz. Next, I have my coaxial cable run out to my NFED transformer, and notice that it's very, very flat. There's no response that jumps up at me here, which means the cable is fairly good. There's no nicks on it, there's no shorts or opens, and the cable run is very good out to the NFED transformer. Get a very, very strong reflection at the NFED transformer at 99 feet out. And if I followed this curve out even further, if I had gone out more than 50 meters or so, I would have seen another reflection that occurs at the end of my 132-foot NFED wire. And of course, the velocity of propagation here is quite different than it is in coaxial runs. Here I'm looking at a coaxial cable propagation factor of around 0.66, whereas in a piece of wire, I would see a propagation of 0.95 the speed of light or so. Let's take a look at another example with the NFED antenna that we had previously. The antenna was designed for 80 through 10 meters, but let's say I'd like to operate it on 160 meters. Can I do so? And what do I need to do to make it happen? Well, first of all, let's look at the impedance that the antenna presents to the transmitter as a function of frequency in the 160 meter band. And as you can see, the trajectory of that impedance lies along this curve here, which is very far from the origin of the Smith chart. And remember that the further you are from the origin, the larger the standing wave ratio. And in fact, in this case, the standing wave ratio is very close to 6 or 6.5 to 1. Obviously, we don't want to operate our transmitter into that load and probably wouldn't be able to operate. It'll probably fold back on us. So what can we do to take this curve and move it toward the center. Well, let's take one frequency as an example. Let's take the center of that 160 meter band of 1.9 megahertz and see what we can do to transform it. First of all, let's look at the Smith chart itself. The Smith chart has a set of concentric circles, and those circles, you can see here, represent a fixed resistive value. As I move to the upper part of the Smith chart graph, in this region here, I'm inductively reactive. In this region, I'm capacitive reactive. And if I fall along any specific curve, I have a fixed resistive value. So as I move along this curve, what I'm doing is not changing the resistance, but the resistive component, but changing the inductive component. If I put a series inductance in my circuit, my point will move clockwise along the constant resistance curves. If I put a series capacitance and in the circuit, then the impedance will move along those same fixed resistance curves in the negative direction or counterclockwise direction. Similarly, I have a set of curves, concentric circles, which represent fixed admittances, reciprocal of resistances. And if I have a shunt inductance, I will move counterclockwise along the fixed admittance curve. And if I have a shunt capacitance, I will move clockwise along the fixed admittance curves. So, thing to keep in mind, anytime I add a capacitance, I'm going to move myself toward the bottom of the Smith chart. Anytime I have an inductance, whether it's shunt or series, I will move in the upper portion of the Smith chart. Now, in order to get the antenna to match at 1.9 megahertz, like I said, I need to move this point from this location here to the origin. First thing I can do, if I add a shunt inductance, and go here and look at this curve, you can see I move counterclockwise. So a shunt inductance is going to move me along this curve here. And what I want to do is move along that curve to the point where I get to that concentric circle, which represents R equals 50 ohms. Because once I'm at that spot, then I can use another component to move myself counterclockwise along that curve to the origin. So what is that? That's a shunt inductance. So shunt inductance, I put in the circuit here, and it turns out that I need 8.288 microhenries to move myself from the 1.9 megahertz point here to a point here at 1.9 megahertz with that inductance. Next thing to do is I want to move counterclockwise. Well, moving counterclockwise is a decreasing series capacitance. Here we go. And so I essentially add a series capacitance that brings me back to the origin. That series capacitance turns out to be 437.1 picofarads. So using a 8.288 microhenry inductance, shunting the coax, and a 437 picofarad capacitor in series with that shunt inductance, I end up with an SWR of 1.02 to 1. And what you'll see here's this little small curve here, but the SWR goes right down to 1 at that specific spot. And from this curve, you can also determine what the effective 2-to-1 bandwidth, things of that nature. Now, as they say, there's more than one way of skinning a cat. So there's a couple other ways that I can reach that center point as well. Here's another example. Remember that moving to the right, or clockwise direction, corresponds to a series inductance. So what I can also do is, instead of hitting the 50 ohm resistive line, which is this curve here, I can also hit the 50 ohm admittance line, or reciprocal 50.02 conductance. In order to do that, I add a series inductor, which you'll see here. And a series inductor of 13.8 microhenries gets me to a point on the conductance curve, which is equivalent to 50 ohms. And then moving counterclockwise in this direction along the constant conductance curve is a shunt inductance. Remember, I'm moving upwards into the upper part of the Smith chart, so it's always an inductance there. And that corresponds to 11.56 microhenries. So sure enough, the combination of a series inductance of 13.8 microhenries and a shunt inductance of 11.56 microhenries will give me a SWR of very close to 1 at 1.9 megahertz. Well, so why don't I use this versus the other one? Well, one thing that's nice about this is that there's no DC, right? Because I'm shunting that out. That may be good, that may be bad, depending upon what I'm trying to accomplish. The other problem is with this approach is that there's only a certain region of frequency where this will actually work. In other words, remember, I'm trying to move from this point on the curve. This is, let's say, 1.8 megahertz, and I want to move in this direction with that series inductance. Well, notice that I could never hit the curve where the impedance or the conductance is, or excuse me, the admittance is equivalent to 50 ohms if I am beyond this point right here, because this point is the last point where I can add a series inductance and get myself to the origin. Once I'm beyond that point, anywhere in this region here, the curves will always miss that point. And no matter what I do, I will end up with a higher and higher and higher SWR. So it turns out that this particular matching network will not work if the frequency is below 1.88 megahertz. Now, the reason that this is particularly interesting is that a lot of people have noticed that when they have a matching network attached to their radio, it may match an antenna. Whereas if they take the matching network off and use the internal matching network of their radio, it just doesn't work. Or vice versa. Sometimes the internal radio matching network will just work fine. But if I add an external matching network, no matter what I try, I can't get it to work. And this has to do with the architecture of the matching network. Certain matching networks will only match certain parts of the Smith chart. So for example, in this case here of these two inductances, a series and shunt inductance, this region of the Smith chart cannot be mapped into 50 ohms. So you need to take that into account when you're designing matching networks, when you're using a matching network, that one matching network may work just fine. You take another one which has a different configuration, might have a capacitor instead of an inductance that's variable, that may or may not match. So it's kind of an interesting aspect of the Smith chart. Okay, I mentioned earlier that not only can we measure things such as SWR and impedances, but we also can measure antenna gain and pattern. Well, this is a little bit more complex, but it's something that is doable at the higher operational frequencies. So let's say I've got a NanoVNA. I've got two ports, port 0, port 1. Port 0 is my transmit port, and that's attached to an antenna to be measured. And port 1 is the receive port, and that's going to be receiving a signal from another antenna through an RF amplifier. If I make these two antennas identical, then I can determine what their gain and pattern are in the following way. So from the Friis transmission equation, this is the relationship between received power and transmitted power versus distance, antenna gain, and wavelength. The transmitted power times the transmit gain times the receive antenna gain divided by 4 pi d over lambda squared, which is this term here, gives me the received power. So the ratio of the received power to the transmit power is S21, and that's given by this equation right here. If I have identical equations, identical antennas, I should say, then the gain of the transmit antenna is the gain of the receive antenna, which I'll call G, and G then can be computed from the Friis equation as 4 pi d over lambda square root of the magnitude of S21. So if I know what the distance is between two antennas, and I know the frequency of operation, a measurement of S21 gives me the gain of the antenna. And of course, this could be done as a function of angle. So like if I put these on rotating platforms, I can then determine what the characteristics are spatially. The range should be chosen to be in the far field of the antenna pattern. So this equation usually should hold. This is the Fraunhofer distance. So the D should be greater than 2 times the largest dimension of the antenna squared over lambda. Also, we have a path loss, right? The path loss is going to affect the signal level at port 1. I need to compensate for that. So, for example, if I have a distance equals 2 times lambda, in other words, I make the distance between my antenna equal twice the wavelength, then the loss is going to be about 28 dB in terms of path loss. So if I add a 28 dB amplifier or 30 dB amplifier, I get the signal back again. The VNA calibration, if I'm going to go with this route, must take into account the coaxial cables, connectors, and of course the RF amplifier gain. Now, the problem with this is that you're not going to build 2 HF antennas and swing them around each other, but you can certainly design VHF, UHF, and microwave antennas. And remember also that you can build an antenna for a higher frequency and scale the results. So for example, if I decide to build a J-pole and I want to see how it works at 144 megahertz, I can build the equivalent J-pole at 1 gigahertz and scale the dimensions and look at the gain and antenna pattern, which is not going to change with frequency, whereas the dimensions will. Well, in summary, in the past, vector network analyzers were primarily used at VHF and higher frequencies, where direct voltage and current measurements were difficult, if not impossible, to obtain. Usually these VNAs were in the 4 or 5 figure range. And in fact, I think the first VNA that I bought for my own company cost me the price of my first house. So they're not cheap instruments. The NanoVNA is a game changer. At $50 or $60 a pop, it's unbelievable what can be done. Obviously, they're not going to have the dynamic range of these very expensive instruments, but for amateur radio purposes, they are extremely good. The VNA, as I mentioned, measures incident and reflected waves using directional couplers, Wheatstone bridges in particular in the NanoVNA, and IQ signal processing to obtain the complex scattering or S parameters of linear 2-port networks. Remember that you can completely characterize a linear system by these 2-port parameters. And like I said, with the advent of these extremely low-cost microwave frequency synthesizers, wideband logarithmic detectors, high-speed signal processors, such as the audio processor that's used inside the NanoVNA, the NanoVNA concept has become a viable option for the average ham shack. But to fully understand and make the best use of the VNA, really a solid understanding of the Smith chart is a great first step. And I've got some references here for you. There's a very nice tutorial on Smith charts by both Rohde and Schwartz and also W2AEW. The software for the NanoVNA can be found at this location here. And the Smith chart processing software called SimSmith is something that I highly recommend that you download and play with. I think you'll learn a tremendous amount about the impacts of various system changes on SWR and impedances, and I think you'll learn a lot by playing with that Smith chart simulation package. Thank you very much for watching my presentation. If you have any questions, comments, please forward them to me at ak3y@arl.net. Also, a copy of the view graphs for this presentation can be found at my website, www.ak3y.com. Again, thank you very much.